Good morning, everyone. Bonjour à tous. It's an absolute pleasure for me to be here today. And I only have 10 minutes, so I will do my best to briefly describe to you some of the work that we've been up to at Algorithmiq in order to forge the path towards commercial value for near-term devices. So I'm Kirsten, I'm the CEO of Algorithmiq. Algorithmiq is a quantum computing software company for drug discovery, and we recently raised our Series A. Now, I think it was mentioned a few times throughout this conference, but pharma companies are facing an R&D challenge where drug discovery is becoming increasingly expensive and risky. And with the last 30 years, we've seen a tenfold increase in the spend for drug discovery, whilst the number of yearly approved new molecular entities remains largely the same, so an overall loss of productivity. We also know that one of the one of the greatest challenges of drug discovery. Here you go. There you go. I just wanted to show you my nice video. One of the greatest challenges of drug discovery, as we know, is to predict with enough high accuracy the binding of a drug molecule to certain proteins in your body, which are responsible for a given disease. And we know, of course, this is extremely difficult because one needs to understand at the atomical level how the drug will interact once it enters your body and interacts with its surroundings. But it's also extremely important to understand this in order to understand the functioning of a drug. To add to this, the gigantic chemical compound space remains largely unexplored and inaccessible to even the most powerful supercomputers out there. This is a space that contains 10 to the 63 molecules, which, to put this into context, is double the amount of stars in the entire universe. However, this space could contain the future key to successful drug molecules for the industry. So how do we start to explore this space, and really how do we harness the power of quantum to bring to the life science industry the breakthrough and disruptive impact they've been waiting for? So at Algorithmiq, we have developed Aurora, which is our state-of-the-art drug discovery platform, which is based on breakthrough quantum software. So what we've done is, in one platform, is combine the most powerful classical algorithms with our proprietary quantum algorithms for chemistry simulation. These are hybrid, which means that we only use quantum for the part of the simulation where conventional methods do not fail, like machine learning or tensor network. So how does this work? It's a three-step approach, and each step requires a complex optimization procedure. But really the key breakthrough at Algorithmiq, and which is in Aurora, happens at the interface between processing and post-processing, where we have discovered and patented a method which combines the results of quantum computation with the most powerful classical algorithms in a way that is scalable, efficient, and accurate. And this is what we call an information complete generalized measurement. And this is really the key to scaling our platform. So information complete measurements are particularly special because you can measure firstly at once, and then later in post-processing, you can decide which are the quantities you want to evaluate. This is extremely powerful because it means that you need way fewer shots on the computer, and you can actually start to almost virtually transform the state in post-processing. Now you can see that this is a full stack of our platform. These informationally complete measurement approach, or ICP OVMs, for those that are more technical in the audience, sit at the lower stack of our platform at the quantum primitive level. And the IC measurements, ICP OVMs, or informationally complete measurements, combined with our noise mitigation strategies, is really the key to scaling our application modules in chemistry and life sciences. And I cannot stress this more importantly, when we're working on near-term devices. This is really the key to everything that we're doing. We also have pioneered a quantum network medicine approach, which is mostly driven by AI and data-driven approaches, but this I will not have time to speak about today, but I know that a lot of pharma companies are extremely interested in this module. So as I said, and now we're going backwards. As I said, error mitigation is an absolutely essential part of near-term devices and near-term quantum computing. And so at Algorithmiq, we've developed a really powerful tensor network error mitigation algorithm, which we call TEM. Now, TEM uses tensor networks in post-processing to counteract the noise. And it's particularly efficient because it's generally much easier to simulate classically the noise that is associated to the circuit as opposed to the circuit itself. And TEM is particularly, one of the greatest advantages of TEM is really in its measurement shot efficiency. So TEM, and we've recently proven this mathematically, is mathematically proven to be optimal, which means that it really reaches the minimum theoretical bounds for quantum resources required when you're using error mitigation. And in other words, it means that it really requires the smallest allowed amount of steps of additional measurements that you need when you're using error mitigation strategy. And this is really the key to this. And there is really a quadratic improvement in this method. When we compare this to other state-of-the-art methods that are out there, like ZNE or TEM, these, of course, are analytical and assessment, but 1 hour of TEM is the equivalent of 1,000 hours of ZNE and 9 million hours for TEM. Now, we're extremely excited about this because it really shows the potential of this method. And it's not just theory, because we do have an experiment, and we have results that we've achieved with IBM, which are unprecedented, and we've presented those at the IBM Summit in December, where we ran, with IBM and our colleagues at Trinity College, one of the largest scale error mitigation experiments ever run on an IBM hardware. Now, this is huge, and we did this with 50 qubits and 98 CNOT layers, where the depth of the circuit reached up to 2,400 CNOT gates, and you can see the circuit on the top right, which is extremely deep. And what we did is look at, and there's not the cones here, it's not come out exactly perfectly, but what we did is we looked at 4 time steps here, which are associated with 4 circuit depth, and you can see that when without using TEM, the signal, which is the round dots, the curve goes down. So there's a green dot, a red dot, a purple dot, and a blue dot. So as when it's unmitigated, in a scenario unmitigated, the signal, which should be at the level of the optimal value of 1, decays because of the noise affecting the circuit and reaches up to 0 as the depth of the circuit increases. Now, when using TEM was able to recover the quantum signal at every stage of the quantum circuit depth. And so you can see TEM is the square. You probably can't see it very well here, but it's the square dots, and TEM was able to recover the optimal value of the signal at every stage. And this really shows the potential for TEM to really start to mitigate noise in large-scale experiments, which is what we want to be doing. And we expect to see quantum utility value on real use cases with TEM in the near future. Now, as I said, this is absolutely crucial for applications to have a powerful error mitigation strategy with our key enablers, which are information complete measurements. And this together is what is enabling us to scale our application. Now, I want to touch a little bit about what we've been up to on the life science side as well. So this summer, we were awarded by the Wellcome Leap a project to work with our partners IBM and Cleveland Clinic on photoactivated cancer drugs. Now, we've chosen a specific class of drugs called photosynthesizers because these drugs are extremely challenging to work with. Because the way that they work is once they're administered, the drug is activated with an external light source after the patient has taken the drug, where the light source shines light on a specific part of your body, which is extremely targeted and tailored. However, it's an extremely difficult process to do because you must understand the ground state energy of the drug molecule as well as its excited state energy when the drug is activated. This means that there are no classical approaches right now that fits all possible scenarios for this drug. So we need a quantum solution here. And what we're looking to do by 2026 is to really describe this framework, where we design uniquely a drug in a unique way that where the drug is able to make use of the external light in order to create radical oxygen species, so ROS, in order to cause the apoptosis of the cancer drug or kill the cancer drug. And it's this process that we're trying to describe in the most efficient and fast way, because if we can start to do this, we can really improve the patient outcome, but also the patient experience, because you can start to, for example, lower the in-cell cancer concentration of the drug in the patient cell, as well as modify the type of external light sources that you're using, such as using infrared, which we know are less harmful for patients, but also have longer wavelengths, which can penetrate deeper into the tissue and target cancer cells in the deeper levels of the tissue. Now, of course, today I'm just the messenger of all this, because this is a great and amazing team that is behind everything that I described today. This was us at our hackathon in Finland, in our headquarters, and really they inspire me every day, and they're an absolute joy to work with. We defined our goals for the year in 2024 and beyond, and we really are, I mean, I would be lying to say if they were not ambitious, because of course they are and we have to be, and we really are trying to push the boundaries of entering the regime of quantum advantage by the end of this year, but also in 2026 with IBM and Cleveland Clinic to predict and simulate a drug with quantum. Of course, Aurora is available for commercial partnerships, so please do get in touch if this is something of interest. Thank you so much for your time and your attention.